And then we have the next scale of test cases, which is the block level tier. And this is essentially to test the scalability of LLMs and being able to fix these violations. We have 7 such block level test cases from open cores, designs implemented with open road flow scripts at high utilization. And these blocks have, if you look at the diversity of DRVs across the 7 blocks, it violates about 17 rule types. The variation in the number of DRCs per block is large, with the largest block having 765 violations and the smallest about 233. This is where we notice that a simple agent prompt starts breaking down, as you will see in our baseline results using these benchmarks. So each test case itself ships like a human engineer would evaluate. So what are the artifacts that come with each test case? So each test case has a GDS2 layout, a K layout Python script that represents that layout. It has layer-wise screenshots and combined screenshots for visual context for the test case. It has a DRC report in a JSON format. It has connectivity information of what are the electric constraints for that specific layout. And it also has the corresponding ASAP7, modified ASAP7 DRC rule deck with our extensions. Including that, we also give it images from the ASAP7 DRM manual for the corresponding violations that particular test case has. Agents must reason across text, code, layout, geometry, and images, just like a human would do. And all these artifacts are there per test case for the polygon level scale, the standard cell level scale, as well as the block level scale test cases. So the benchmark itself evaluates 2 tasks. In detection, the agent gets the layout and the rule deck, not the DRC report, of course. If prediction, it gets, for the task of detection, it gets the block, it gets the layout and the rule deck, and not the DRC report, of course. It has, the task is to predict the violations in the region and their corresponding rule types. And the metrics that it evaluates, the evaluation harness evaluates are precision, recall, F1 score, and accuracy. And a prediction counts as accurate only if it finds the DRC violation within 10% of the ground truth. The more interesting task is the DRV repair task. So given a layout, the rule deck, DRC report, and the connectivity check, we're asking if an LLM can edit the layout, the script that represents the layout, so that the violations go away, simple as that. And the metrics include repair rate, new violation rate, and preserving connectivity is a hard constraint. So the evaluation harness we developed prevents any kind of cheating from the LLM. For example, in the detection task, the agent cannot simply use a DRC analysis tool to locate the violations. For the repair task, the edit script regenerates the layout, the evaluation script regenerates the layout from the generated Python K layout script, checks for connectivity, and only then does a golden DRC simulation to figure out what is the repair rate and the new violation rate. If the script fails, the GDS is invalid or the connectivity breaks, then that does not count as success for the agent. So for the baselines, we've paired, we create baselines for both the tasks, for the DRV detection task as well as the DRV fixing task. And these baselines are simply taking the input artifacts that we specified earlier, providing it to an agentic flow, which includes a model, a state-of-the-art model, and the corresponding infrastructure around that model. So these flows are a CLI harness along with the corresponding LLM for that. For example, Claude Code with Opus 4.6 or Sonnet 4 or Sonnet 4.6 that is another model, Cursor with Opus 4.6, Sonnet 4.6, so on and so forth. So we've created 7 such baseline agentic flows. And we go through each of these tasks, both the detection task and the DRC fixing task. And the complete results of all flows are provided in the appendix of these slides and also on our GitHub repository. But I'll present a few results on few sample test cases from each of the, or a few sample test cases spanning both polygon, cell level, and block level test cases. So here's the current state of what agents can do. On polygon level test cases, F1 and detect for both detection and repair tasks, the F1 score and repair rates are very high, which means the problem is essentially solved. The rule knowledge is being able to, the LLM is being able to understand the rule knowledge. On standard cells, Performance on standard cells, detection as well as fixing tasks, the performance of agents becomes uneven. So the flow is unreliable across test cases. Some blocks are able to be, some standard cells are fixed completely, some aren't across various agentic flows. On block level test cases, however, detection mostly collapses and repair often produces invalid layouts or new violations. So the takeaway here is not that agents cannot help, it's that block level DRC repair needs structure beyond a simple prompt asking it to fix it, even with multiple iterations. So the takeaway here is that seems like the polygon detection and fixing task is solved. LLMs are able to understand the rule-based knowledge. Standard cell problems are mostly solved, but there's no flow with a simple prompt that can fix it across all test cases. But the block level DRC fixing task is still an open problem. So part 2 of our talk is, the fact that the block level is still a problem is what motivates part 2 of this talk. Part 2 is Evo DRC, which is our approach to fixing these block level DRC violations. Our approach is motivated by the way human engineers fix layout violations. They reuse strategies that worked before, they refine them when layout exposes a new interaction. For instance, if I'm a DRC engineer in a company, I learn on my first block, I fix a few DRC violations. I gain a set of skills that I perhaps write down in my notebook, or I take notes in my head on how I fix DRC violations. I then apply the same set of skills to a new design or a new block and try and fix DRCs in the new block. So the knowledge lives in a personal notebook of what worked and what not, but this is manual, slow, trial and error based method that takes a lot of time. Inspired that approach, we have this idea known as skill evolution. We use an initial reference design, fix the DRC violations on that, and generate skill files on that, which I'll talk about in a little bit. And the idea is just like how a human's skills would evolve, we evolve the skill file of the LLM in order to help it fix DRC violations on a new unseen block. So let me go through this process. So a skill file holds what we know about preparing DRCs per layer, the strategies, suggestions, and even fixes that have been proven to work. So how do you create this skill file? We take a dearly written layout, fix it by hand, and show the LLM both the original layout that had DRCs and the corresponding fixed layout that does not have DRCs, and ask it to write out a skill file, write out strategies, suggestions, and proven fixes per layer. We then use this skill file and transfer it to another design. Apply it on an unseen design. The agent starts with experience from that skill file instead of a blank prompt. It keeps what verifiably worked. Every repair is checked, and the outcome is then recorded. And then based on its interaction on that design, it evolves the skill file. It improves on what worked and what did not work, and then that is the skill file that is provided to the agent to continue to fix its task. So Evo DRC itself first has two parts. The first part is decompose the block. A full routed block has too many violations, and it cannot possibly fit within an agent context. So nearby violations are clustered into bounded crops. Each crop is small enough for an agent to reason about and independent enough to run repair iterations in parallel. One agent repairs each crop using the relevant skill files and edits the skill files based on its interaction with that particular crop. The edited crops are then finally merged back into a full layout. What happens at each iteration with the crop? After each crop is repaired, Evo DRC runs DRC analysis on that crop and also checks for connectivity. It then records only if verified outcomes, what the edit fixed, whether it introduced new violations, and what cost it incurred. Finally, it evolves the skill files using those recorded outcomes. What the skill file contains are new situations that are added based on its interaction with the new block, what new geometric context it saw, what warnings grew, perhaps some particular change that worked on another block did not work very well on this block or made things worse, and what suggestions get pruned. Perhaps advice from a previous block was not very applicable to this block and must be deleted from the knowledge database or from the skill file. So using this approach, I'll present a few results, and These results here show repair results on the block level test cases of the benchmark I presented earlier. So this has 7 blocks. So what each bar shows is it shows normalized DRV count to the initial number of DRVs present, and it shows the DRV at each iteration, and we've performed 5 iterations of this EVO DRC loop that I talked about earlier. So you notice that compared to the number of, it's been over multiple iterations, it's been able to reduce the DRV counts, and this each iteration, the DRV counts are calculated only after we've taken the crops and merged it back, right? So compared with the original baseline that we had presented earlier, with all those different CLI agentic flows, we were able to, on the 2 block level test cases I presented earlier, EVO DRC was able to remove a lot more violations compared to the baseline. So if you look at the bottom left corner there, on block 5, compared to the baseline, which removed only 31 violations, but it introduced over 144 violations, this technique of skill evolution removed 68 violations and introduced no new violations. And on block 7, which is the largest block that we deal with, the initial baseline removed 482. EVO DRC was able to remove about similar number, 490, but it did not introduce any new violations. On an average, we brought DRV reduction down by 83.6% across all the 7 blocks in the benchmark. And the cost was quite significant, an average of $150 per block. So we also looked at a few ablations to see the impact of the skill evolution framework and the ability of transferring skills from one design to the other. So the first one here shows that on average we reduced DRV. This is full EVO DRC. We reduced the number of DRCs by 83.6% compared to the initial starting point. So the first ablation that we did is no reference design skill file, which means there is no starting skill file that we learned from the reference design. And in that case, performance dropped significantly to only 51%. We then had another ablation where we used an initial skill file from the reference design, but we did not allow it to evolve over time as it interacted with the new design, new benchmark. And in that case as well, performance dropped by about 6 to 7%. And the third is the idea was we removed that layout decomposition approach where we eliminated the cropping strategy and tried to solve the entire layout at one go, and that brought down our performance as well significantly, which shows that each of the different components of our EVO DRC framework actually contributes to the final result. All right, that brings me close to the end of the talk. This is part 3, is how we turn this into community research, not just one paper and one method. So using these benchmarks, yesterday at DAC, we had the ICLAD DAC 2026 Gen AI Chip Hackathon. 6 teams worked on this problem. There were 2 tracks. There was an on-prem resource-constrained track, which you had smaller limited tokens, smaller models that are present on the edge. And there was a cloud track, which had all the frontier models. The task was the same, benchmark style repair problem, return a clean layout that still implements the same circuit. The scoring metric, though, was updated a little bit to what we've been looking at. It tries to take in token cost into picture, and we came up with this metric of number of DRC violations fixed per million tokens used. So it tells you how efficient your agent is in fixing these violations and can give you some comparison between different teams and evaluate the efficiency of your approach. So teams were rewarded for the number of DRCs they fixed to the total number, to the model cost or to the token cost. So to conclude overall, there are 3 takeaways. There are 3 things that I presented today. I presented a benchmark, what this paper's primary contribution is for DRC-related challenges in digital VLSI circuits. I presented a research method named EVO DRC that relies on this concept known as skill evolution. And the third, I presented a use case of us opening up this problem to the research community via the ICLAD DAC 2026 hackathon. The GitHub links for all of them are available on the slide here. I want to conclude by 2 key takeaways. First, community-driven research needs shared ground. Benchmarks, open evaluation harnesses, and perhaps a contest to turn a problem into something multiple groups can solve. with the same infrastructure. And two, benchmarks need to keep getting stronger. We built this benchmark with one baseline, and over the past 3 months, the models have changed over time. 3 months from the release of these benchmarks to the hackathon today, newer models were already fixing these problems fast. So we need stronger baselines, stronger benchmarks, which need to be constantly updated. And just like the other two talks, it's a call to action from the community. Thank you so much. Right. So when you merge the layouts, there is a possibility of a conflict. I didn't go into details of that. The details of that are available in the archive paper. But there are approaches in which we actually, once we have the conflict, we have something called as a skill judge agent that looks at the conflict and decides which one was a better fix in the context of the entire layout. So we have that one call when we would bring them both together to the skill judge agent.